Hi, Mr. Richmond here with your section 1.3 lesson summary for Math 1. In this lesson we're going to be working on recognizing algebraic and graphical representations of functions. In our last section we learned about what a relation is. It's a comparison between two quantities, usually our x or y values. We've talked about what an independent quantity is and what a dependent quantity is. Independent quantities being our inputs, dependent quantities being our outputs, and that the independent quantities typically go on the x-axis and are our domain, and dependent quantities go on our y-axis and are our range. So here now we're going to take a look at some typical equations that we've seen, things like y equals 2x plus 5, where typically x has been your independent variable. It's been the one that you plug things in for to get an answer for y, your dependent variable. Well, if a relation is a function, which in this case it would be, because every time I plug in something for x, I'm going to get only one answer for y, I can actually represent them in a more efficient way called function notation. The advantage to function notation is I get to see exactly what my independent variable is, as well as my dependent variable, and also when showing work and working problems out, I can see exactly what was plugged in as the input or the independent variable in the problem. So to change something from a regular equation to function notation is actually rather easy as long as you know what function notation is. It's just taking that output variable y, the dependent one, and writing it in function notation, which we read this as f of x. Okay, and it doesn't always have to be f of x. You can choose these variables. I could go s of t. Okay, in that case, the f would kind of be the output variable, that'd be my dependent. And whatever you have in the parentheses here is the input. It's where you're plugging values in. The rest of it would stay the same. So I have f of x equals 2x plus 5. And now in a case like this, I can plug numbers in. I can pretty much do whatever I want. If you ask me, hey, what's the input to this when x is 3? Well, I can represent that. If I want to plug a 3 into this, and what's nice is I actually just change all the x's in it to 3, and I can show my work a little better and let people see actually what I plugged in and what my answer is going to be. Keep in mind this is f of 3. This doesn't mean any form of multiplication. That'll stay f of 3 because it's just a notation. It's just letting the reader know that that's going to be my answer for an input of 3. Then I can work it out. 2 times 3 is 6. 6 plus 5 is 11. And I can say now, the answer to this function, or the output to this function when the input is 3, is 11. Because when I plug 3 into 2x plus 5, I get 11. So it just gives the reader a little more information as far as what you were doing in a problem. And again, I can do this for any value of x I want. Okay, we've talked about graphs quite a bit too, increasing, decreasing, things like that. We talked about U-shaped graphs, V-shaped graphs, linear graphs, curves, discrete, continuous. We've done a lot so far. I'm going to add a little bit more to that. A term called absolute maximum. An absolute maximum is a graph that has a y-coordinate that is greater than the y-coordinate of every other point. On the flip side, we could have an absolute minimum. That's a graph that has a y-coordinate that is less than the y-coordinate of every other point. Well, this happens in 2 of our graphs we've already seen. If you look here, we have our U-shaped graph, okay? And here we have our V-shaped graph. In this first one, if I look at the points, there is a distinctive max kind of height. If I was imagining this being the movement of something, it never goes above this. Okay? When you can see that there's never a point it goes beyond, that would be an absolute maximum. So I could say, in addition to the many other things we learned in the last section about this, I could also add now to that, hey, this has an absolute maximum. There's a point it goes to. Okay? In my V-shaped graph down here, I can look, there's a lot of points, but there's a clear-cut lowest point right here. Okay? It never goes below that. So that would be the absolute minimum of this graph. And you can see here that we could do it with discrete or continuous graphs as long as it's clear that if things kept following the pattern that you see, that it would in fact be an absolute maximum or an absolute minimum. Okay, so now that we've kind of added those concepts to what we already know about graphs and how we describe them, let's come up with a more formal definition of each of these types of shapes. So we talked about straight lines, curves, V-shapes, U-shapes, etc. We want to give them now a formal name. So some of these we may know already, some of this might be new to you, but we know this is an increasing graph. It's a straight line, it's continuous. Any straight line that you have like this that doesn't change in any way, we call linear functions. And at this point now, I want to have you start learning the function family names for these. Okay? That is a linear function. Okay? We'll also start to work on the forms of these. This will typically look like this, ax plus b. And all these equations I'm going to write, y and x are going to always be there. That's our input and output values in these equations. I'm not going to write this for all of them because it stays the same for all of them. X is our input, y is our output. And again, if I want to write this as a function, it's as simple as changing the y to an f of x. If the problem asks you to write it as a linear function instead of a linear equation. But for now, I'm going to keep it yx. I think you're a little more comfortable with seeing that. And a and b are just going to be different numbers that you could have. If you look back at my first example, since this is a linear function, well, by looking at the form here, ax plus b, 2x plus 5, numbers are in the spots for a and b. A is 2, b is 5. This is a linear function. I can tell from the equation alone. And our hope is that by the end of this chapter, you'll be able to recognize the function family that a function or graph belongs to by looking at either the equation or the line or the picture or the graph. Okay? We should be able to tell both ways. Our second one, when we have a curve that is coming from real high and curving down low and flattening out, or starting flattening out and curving up steeper and steeper. This was kind of that idea that something was going faster and faster or slower and slower. We can tell by the change. This is called an exponential function. And exponential functions happen when you have an exponent, hence exponential. So its equation would look more like this. A times b to the x. Your variable x, your input's actually an exponent. So when you choose values like 1, 2, 3, 4, you're choosing exponents and plugging it into the function. Our next one is our U-shaped graph. Okay? Instead of calling it a U-shaped graph, now we're going to give it its formal name, which is a quadratic function. Quadratic function. Now it's called quadratic because exponents to different powers have different names. So something to the second power in math we typically call quadratic. So all of these functions will have an input value that's being squared. So there's several different forms that we actually learn for this, but for now it'll be this one. Y equals ax squared plus bx plus c. So you have a number in front of an x squared term, you could have a number in front of an x term, and you could have an additional value that you're adding. So something like 2x squared plus 3x plus 7. Doesn't have to have all these components. The key is it has to have at least this ax squared part. Okay, our V-shaped graph. We talked about V-shaped graphs before. Now we have a formal name for that. That is our absolute value function. Absolute value. And our form for that will be A times absolute value bars plus C. So we should know absolute value by now already. Absolute value of 3 is 3. Absolute value of negative 2 is 2. It's the distance the number is from 0. In an equation, in a graphical representation, the formula would look like this. The equation would look like this. It would be A times absolute value x plus B plus C. And the key there is if you see these absolute value bars, it is going to make an absolute value graph. So it'll make this V shape to it. Okay, but now when we see a V-shaped graph, we're going to call it an absolute value function. See a U-shaped graph, quadratic function. Now our last one is a little tricky because it's not really any of these four alone. If you look here, I have pieces of functions. Pieces. I have a piece here, then it changes, and then here. When you have a function that isn't keeping a general form but is changing a lot, and it looks like it's using pieces of each function, we call that a piecewise function. Now, you can have different types of piecewise. I can actually have some that are linear, and then all of a sudden it turns into a quadratic, or it could be linear and then exponential. There's a lot of different options here with these piecewise functions. For now, in this class and this year, you're mainly only going to see linear piecewise functions, because it'll be all linear pieces. And now writing the equation for that's a little trickier because it depends. It's actually going to have three different equations. I'm going to have a linear equation for up to here, and I would specify that. I'm going to have a linear equation for the horizontal part, and I would specify that. And then I have a linear equation for the end part. So I'd actually have three separate equations going to this one. So I'm not going to write a formal example there, but you can see more as we move in through the text. Okay, hopefully this clears up some any confusion you might have had with this. Make sure you're taking the time to memorize each of these function families, both by its picture or its graph, as well as its equation. Okay? Thank you and good luck.